Well, I'd like to welcome you to the 2024 meeting of the Physics Monastery. This is a big meeting for us because we have a lot of progress to report, and I think you'll find it stimulating at the very least. Just to give you a grounding on where this comes from, if we think back to Einstein and his characterization of the universe as being parabolic fundamentally, where does that go? Well, he developed his equations and his theorems based on a thought experiment. You know, that's quite a famous thing. We decided to follow in that model, and our thought experiment is intended to give us a window into the fundamental characteristics of the constants of nature as defined within the physics and world that we all know and love. And the basis of it is that we assume a simplest possible universe, which is a superfluid, a vast expanse, no edges that will bother us. It has waves, frequencies, agitations, but there's nothing permanent in it. And if we, as a first principle approximation, we say, well, what is the simplest persistent structure that could exist in that kind of environment? Or is there one? I mean, if there's not, then we wasted our time. But we're going to assume that there is one, and the question is, can we find it? If we find it from first principles and basic features of the hyperbolic systems, can that tell us? Can that tell us anything about the constants of nature and how all of this works? And with that, I'll turn it over to our lead scientist.
All right. Well, thanks everybody for coming for our Physics Monastery Fall Conference. This was really exciting because we have a very large update this time. As you know, well, I'm going to start with an overview of what we're trying to do and a review of how we're going about doing it. But then I want to get to the results we now have. So the big story is that CODATA has recently updated all of its measurements, all of its coherent claims of what the measurements of our fixed constant features of reality are. And in several cases, we got another significant digit in several cases, which is a big deal. And with that extra information, and with that refined information, we've gone through the whole set of parameters again to look for the pattern in the constants of nature. And now we believe we've finished finally. Let's start from the very, very beginning here. Let's talk about why this is even important, more in the ontological sense. So the whole start of the story for me is way back in history where the first human became the first scientist by deciding magically that they wanted to understand the world better than the story already in their head. And they wanted to do it in some reliable way that they could trust. And they imagined how to get in a reliable way to peer into the world. And it was to make a measurement. Right? Measurements are more accurate than your first guess perspective. And this was Anaximander, of course, the guy who invented maps, the guy who invented making representations of things in that way. And
technically, it was his teacher.
Okay.
Technically, it's often attributed to him, but
it's pretty shoddy records all the way back, but still, yes. And also, what else did they invent? The early form of the sundial, which is the early form of a clock for measuring time. Of course, just like a gnomon, it's a stick standing straight up, casting a shadow, and then you can measure over time where the shadow goes, right? It gives you a way to measure time. It's crude, sure, much more crude than the ways we measure time now. But it was the first way of making a measurement. And then he would rely on these measurements to interpret the world around him. Now, we're all born into a world where people have done this for us already, right? All the smart people we had talk about in school, the whole history of Newton and Einstein and so on, a whole long history of all the mathematicians who have come to observe things in their mind for the first time, then communicate that notion to us, and now we can all observe them. But before that happens, we're all stuck observing other things. So this is a story about the history of perspective, really, for me. The story of consciousness awakening is a quest to go from somebody who tells a story about the world they're in that's wrong to less wrong and less wrong and less wrong, and if possible, eventually accurately right. And as you get more accurately right, as we've noticed through science, we gain new powers. It's very similar to like a video game in the consciousness sense, right? You literally gain new powers, things you can do now that you couldn't do before, reliably over and over, right? Computers. All of us know exactly what this means. There's so many things now that didn't exist back when our grandparents were around that allow us to do things we couldn't do before. Of course, the projection of where we're going with that is that eventually, when we understand how atoms connect and how atoms reconnect and transform and all the relationships between atoms, then we should be able to do on purpose, just like we store things on purpose on our computer and then can reliably come back and access them. We should be able to do all the things that biology does on purpose. Now we can access those things now, right? We grow crops, we make things, sure, but we don't do it with an understanding of what the atomic structure is doing. We don't do it with a clear, crisp understanding of what the, say, manifold of the structure that you're talking about is shaped like. We don't have a crisp picture. We don't have a crisp understanding yet, and that's what we're after. So our project was to start in similar to the way that, say, math has unfolded. We discovered really cool concepts like, say, the Platonic solids. Okay? And the Platonic solids are really cool because when you first hear about them, you note they're the only way that you can periodically tile the sphere, right? And periodically means you do the same thing over and over and over. So if you want to make a simple system that does one thing but can repetitively do it, but then comes back around on itself, those are the shapes that have something to do with that. Okay, and there's some sort of quantization going on and just being that set of shapes, 5 really mysterious shapes. And for thousands of years, people have realized that these things were mysterious and important and somehow connected to the structure of reality. Many people got a strong sense. Some people were very forward, saying it's very directly connected, like Plato, right? But this has been an ongoing thing for a long time. Most importantly, the shapes themselves have been directly studied by individuals regularly, religiously, looking for the further clues and the further connections. Along comes Euler, 2,000 years into this game, okay? And he's young, introduced to these shapes. And the first step for him, after the awe, was to try to quantify the features of the thing that he was now in awe of. Okay, he wanted to put down numeric features that told him about the object we were now in awe of. What are the numeric features of the Platonic solids?
Faces.
The number of faces each one has, that's a fixed number for each solid. The number of edges and the number of corners or vertices. The angles are also features. Good. So he just listed the fixed features, wrote them down. Now, these aren't things we can all debate. Those numbers aren't arbitrary, right? We show you the cube. How many faces does it have? We will all agree. It's a fixed number. So he just wrote down the list of the features. And from that step, was able to see a connection no one had ever seen before, as far as we know of, that had written down and been not lost to history. As far as we know, he was the first one to know that all of those features are connected. Okay, and this very famous equation is sometimes called the second most famous equation. He also gets the first most famous equation in mathematics. So I'm not going to start writing things down yet. But in parallel to that story, what we want to do in physics here now is we want to take all the features we are in awe of, the measurements of the fixed ingredients of the world, the things that the atoms that make up the world can do. They're fixed transforms, you could say, or their fixed properties. The speed of light, the gravitational constant, the electric constant, magnetic constant, Boltzmann constant, the whole list of 288 constants of nature that we've measured out a certain accuracy each with error bars. We want to know What are those features telling us about the world? What's the pattern in them? Okay, so the analogy is, it's more complicated in the sense that we have, instead of 5 photonic solids with a small number of fixed features that you put in comparison, we now have 288 constants, 288 puzzle pieces that you're looking for the pattern in. And we're going to look for the pattern in it in this systematic way. We're going to write down all the measurements of every single constant in nature. The string of digits gives you the magnitude of the measurement and the dimensions that it's in reference to. It's a magnitude of a certain kind. Okay, so we're going to keep track of the kinds. How many kinds are there? What are they made out of? What relationships are there between the kinds? And what about the numbers? What relationships are between them? That's what we're going to look for. And we're going to look for it in a way that's quite traditional, it turns out. We're going to assume, of course, that the entire space that we're interested in is hyperbolically bound, which seems to be the only actual options. The hyperbolic spaces can characterize an infinite number of choices. You have this hyperbolic conic structure for all of them, but the scale is still a question, like what angle is the cone actually coming together at? In hyperbolic space, no matter what scale you pick, there will always be a scale you can zoom into to look like it's a 45 cone. There will be one specific scale in there in which it looks like this. Well, it didn't draw perfectly 45, but imagine it was 45. But if you zoom out to any other scale, it won't look like 45. Okay. What else? There's other features to hyperbolic space. We got not just the conic structure, but we have this single sheeted hyperboloid that goes around all the way behind and forward, okay, the cone. And then we have this double sheeted hyperboloid here that goes inside the cone down there and inside the cone down here. And there's a gap between these two cones. You can imagine if you squeeze this down, then the cones have to get wider. If you stretch them out, make the gap longer, then the cones change their angle. So the scale at which the symmetry scale happens at 45 would be different, depending on the gap. Okay? But the gap change is the only thing that changes in our hyperbolic structure. This relationship of conic balance, the double-sheeted hyperboloid, and the single hyperboloid are all in every hyperbolic structure, no matter what gap size you want. Okay, we're going to assume, of course, you can describe this structure by deciding I want to stick to this boundary here and describe the whole system, making it my reference, or the cone, or the double-sheeted hyperboloid. Now, the square root, or say half of the double-sheeted hyperboloid, so just 1, is the Dirac equation. The Dirac equation assuming that there's a symmetry balance between all of these exchanges, and there's a unitary system that they balance for, but that there will be a boundary, 5 specific boundaries, in all the connections of space, time, charge, mass, and temperature that satisfy this perfect balance. So the Dirac equation stipulates that will be, and then we find the constants of nature that actually do match up to that balance. Okay. All right, we start from there. So this is the classical system of what our system is. And now we're going to stipulate a very specific scale for our hyperbolic space. So we're going to go from here's hyperbolic structure in general to here's an exact hyperbolic space. And then we're just going to characterize the partition structure of that hyperbolic space and show that we're going to use that partition structure to look for the pattern in the constants of nature. There's a good way to say it. So we're going to have one system that's this exact hyperbolic structure with a very specific scale picked to it. And it's going to characterize, it's going to choose for us the hyperbolic parameters or the partition parameters of the hyperbolic space. And that hyperbolic breaking up structure, we then look for to see if there's any connection between it and all the 288 parameters in the constants of nature. And it turns out that the pattern is astonishingly simple to see. I mean, you don't have to know what it means to see the pattern, is what I'm saying. You could not understand a single character and say, I see a pattern here. It's beautiful. So the way we're going to get to this is we're going to assume that the internal hyperbolic structure, there's internal and external in the balance. Okay? Kind of like when you're making a hurricane wall. You've got an inside and an outside of the wall that are both coming together, the same thing. The internal system is going to be the smallest possible 3-manifold, the Giesecke manifold, but double covered. So we're going to use the smallest manifold you can possibly make in 3D. and we're going to use it as its own anchor. We're going to cover it by itself and make it the smallest possible anchor you can make, because we made it out of the smallest possible manifold. All right, so that would be a symbol for that is the Giesking, GGI. There's a number for the Giesking constant, like pi is a string of digits. We're going to get to these numbers. Right now I'm going to just start with familiarizing with a little bit of the constant symbols. If we times the Giesking constant by 2, so GGI times 2 equals the hyperbolic figure 8 knot. So the hyperbolic figure 8 knot is now defining the smallest possible internal hyperbolic knot, making external hyperbolic space. What's the equation for the hyperbolic figure 8 knot? There's several ways you can write this. This is the way that I think is most informative for me. I, the imaginary unit, we define that here, square root of -1, or not write it like that. It's going to be easier to write it like this. -1 to the 1/2 times by a dilogarithm, two-dimensional logarithmic connection, or a polylog connection, of 1 over the imaginary golden ratio. Better handwriting, please. And the imaginary golden ratio is equal to -1 to the 1/3. Okay, and then we're going to subtract from this another dilogarithm of the exact same kind, but this time invert the argument to just the imaginary golden ratio. And there we go. This is a logarithmic, a hyperbolic structural argument for getting the hyperbolic figure 8 knot. Now, once we have these arguments of the imaginary golden ratio and 1 over the imaginary golden ratio, making our internal structure, but it's double covered, so the outside is going to be a reflection of that. We now want to go from this to talk about the outside structure. So this is the inside structure, the whole story, really, at this point. We're going to go now and ask, if you have this internal knot, the smallest hyperbolic knot you can make, what hyperbolic structure on the outside do you then have? So to get there, we just look for the hyperbolic reach, which you can characterize as the equation 1 over x plus x cubed. This is just the equation of the unit hyperbola. Okay, so, excuse me. So we write down the equation of the hyperbola, but we want to then say, set this equal to 0, because I want to know what its roots are. What are the roots of this hyperbolic simple reach? And it turns out when we solve for x, we get x equals the imaginary golden ratio, 1 over the imaginary golden ratio, the imaginary golden ratio squared, and 1 over the imaginary golden ratio squared. It has 4 roots now. Internally, these roots, we're keeping it closed. Externally, we have this structure that gives us those roots. All right, but when we were assuming this, we started with, give me this simple hyperbolic reach. But it's also, how far does that reach go? For this hyperbolic curve, it goes out to infinity. Now, we don't want an infinite structure happening from a finite gap. A finite hyperbolic gap on the inside should have a finite, no matter how big it is, it has to be finite reach. Okay, so we need to modify this infinite hyperbolic structure to a finite one, and we need that finite one when it finishes reaching out. What it's done is it's turned itself inside out, because then the other side is just starting over and the whole thing continues and continues and continues. So those conditions can be reached by modifying our hyperbola in one simple way on the left, saying that the volume complement is divided by a circle. This is turned itself inside out when it's reached out to its end. That's another way to say that. Here's how we change the right-hand side. So instead of saying its roots for a hyperbolic structure whose gap is 0, the infinite hyperbolic structure only, we want to now give a gap. We're going to break it apart and give it some positive gap. So now we're going to say, and inside that gap, we're going to still maintain that it has to have this 45 quaternion logical structure of hyperbolic space. So we can characterize that 45 degree on 45 degree intersection like this. And then we have to have some sort of mass gap, just to characterize the scaling parameter for a whole hyperbolic structure. We're going to use the Planck mass. The Planck mass, because that's the one that's in the Dirac equation. That's the one that hyperbolically makes that all work. And because it's one of the boundaries, and because this is the mass gap. You're only really getting to pick from the Planck time, the Planck length, the Planck charge, the Planck mass, or the Planck temperature. So the mass gap should probably be the Planck mass.
Through all the constants of nature, is there a way to reduce the information given into a simpler form?
Oh yeah, fantastic. Okay, actually I'll do that very next. Because first I need to finish saying in this some very important feature, is that now that we've modified this hyperbolic structure to be finite and turning itself inside out, but still maintaining the rules of hyperbolic space, but set to a very specific gap that we care about, these solutions change. They have to, right? It's not the same equation anymore. So it has to be something different than the imaginary golden ratio. Now, what we're interested in is, what did this change to? What did that change to? What did this change to? And so on. So we can ask Wolfram alpha, solve now for this new equation. What does this new x mean? These different x's now, right? And now we get that the solutions are the number we call this, J1, J2, J3, and J4. Okay? Now, everybody here has already seen me do this a few times, so I'm not going to draw everything. I'm trying to go a little fast through this version, just a little overview. But those are now the partition solutions to our finite hyperbolic structure with this very specific scale. Okay? That's just all they are. I mean, in the exact same way that these were the roots to the infinite hyperbolic structure. Okay. And also, you can kind of see a direct connection between the hyperbolic figure 8 knot all the way to the outside condition, I hope, here. Certainly you can see it from that step to this step. Okay. I'll come back to talk about this partition rules that come from these partition constants in a second. But now we're going to switch to basis for a second. When we want to ask this partition structure, how many ways do you break up? What do your boundaries look like? What scales are those intersections? What kinds of boundaries are intersecting, and so on? When we want to get that whole story from this exact structure and pair it to the constants of nature to look for, is there actually any information to distract you? Is there a pattern that shows up now? It turns out that we have to look first at all the actual listed data points, all the constants of nature at CODATA, okay, recently updated. Those constants only are composed ultimately of 5 bases. Okay, they define a manifold that's dividing up in 5 completely different, unique ways. You could follow each of them individually and think it's a different story, and then start the same system at the scale of 1 and divide up a completely different way if you divide in the other base. And all 5 of these bases divide up the system under balance. They need all 5 to balance against the others. Okay. In fact, it's under this balance specifically, right? A 4-dimensional balance for 5 bases, the 5th being the gap size. Okay, those are things we end up giving labels to in our system. Bases for time, and at this point it's a label. I want you to think of it as abstractly as you can, okay? Time is the most refined breaking up of bases. It breaks the system into the smallest pieces with the most number of pieces, okay? So it's the highest resolution base of your manifold, okay? And it has a 1. The same 1 as every other base, because the 1 is the projection, the whole balance, okay? It just divides up the balance in a different way. And that's the first way, the most highest resolution. The next way is we call space. And then, or length, charge, mass, and temperature. Now, these are literally just bases of one system. They're all required. It's a 5-dimensional balance. the system is literally going to be describing these bases in physics, but it might be easier to start just thinking, all right, time is a base, a balance, a base of the system. It has a 1 associated to it. There's a 1 in the projection. There's the balance of the whole thing. And the way time divides up 1 is going to be different from the way space divides up 1 or the way charge divides up 1 and so on. All right, but if the 1 is the balance, that means everything else is numerically going to be a field. It's going to logically maintain some connected rules. All right, if we look at the Planck constants for each of these boundaries, Planck time, Planck length, Planck charge, Planck mass, and Planck temperature, we can use those boundaries and put them together, divide them, multiply them in all different kinds of ways. And it turns out that the constants of nature do exactly that. Constants of nature are built from all the relationships you can make in the Planck constant boundaries of these 5 dimensions. The boundaries of the thing that's dividing up. Okay, so what we're trying to do in this project is get a picture, to build an exact, not a vague picture, but an exact precise picture of those 5 boundaries in our precise hyperbolic space with an exact set Planck mass gap. All right, we're almost going to get to look at the pattern that we're at, which is quite exciting, but before we do, let's remind ourselves one more time at some of the interesting connections of this partition structure. First connection is we want to look at their sum. Whenever we do this in algebra, we got roots of something, we want to look at the sum of all the roots. 3 and 4. We also want to look at the product of the roots. I'm not going to write times if you just put them next to each other, same thing. Equals, equals. And then the quadrants. Quadrants is you take each one and square it and add it together. And this tells you historically the geometric connection structure. Sorry. Did you guys see that? Yeah. It's hard to talk at the same time because you moved on to the next thing. This tells you the geometric structure of your connection, in your geometry, right? That's the just traditional way of looking. In our system, if we put J1, 2, and 3, and 4 atom, we just get our balance of 0. If we multiply them, the product is 2 pi, and if we take the quadrants, suggesting it's telling us what sort of system are you dividing up 4-dimensionally, quadding, we get negative 4 pi. So our hyperbolic structure eventually becomes what? When it goes out to its infinite or its finite reach, it's now a sphere. Okay? It's hyperbolically bound on the inside. All of its conic structure on the inside are hyperbolic boundaries. But that hyperbolic structure itself, because it's finite and inverting eventually, that boundary up there becomes just a sphere. A boring, beautiful sphere. Okay, another interesting feature is if you take all of these solutions and find every pairing possible, every byproduct, and add them together. So what we can do, J1 times J2, that's a byproduct. Now I can still do J1 times J3. I can do J1 times J4. Now I have to move on to the 2's, right? J2 times J3 plus J2 times J4 and plus J3 times J4. Okay, we added all the byproducts together. Again, we get another circle. Now remember before when we were thinking of a hurricane or a hurricane wall, think of it as kind of circular. But on the outside, you're going to be coming to a circle, and the inside you come into a circle. Even though the radius of the circle might be the same, there's an outside and an inside. Here we got 2 different circles we're referencing here, in our simple product and in our byproduct sum. 2 circles can come together from the outside and the inside. I'm trying to get you to start visualizing the partition structure a bit. It's going to have a throat on the inside, and that throat's going to be a circle. Very simple, the unit circle. But we got 2 references to it in our partition structure right away. Now these are exact identities. They're not like approximately, it's the first 3 significant digits. No, all. Okay, these are geometric numbers like pi, because look, J1, 2, 3, and 4 have a very vivid relationship with pi in this way and in this way and in that way. Those are all pi numbers. Okay. Now I want to look at the possible partition structure of the whole system. This is the, of the partial systems. This is the whole structure. So by whole structure, I mean, in this equation, I have referenced every je, 1, 2, 3, and 4. What if I wrote 1 plus 2 plus 3? Now what is it? And so on. So I want to now reference every partial equation, one that doesn't have all 4 of them in it. You can have, but it has to be plural. It needs to be 2 or 3s. Okay, so all the 2s or 3s that what? That give us a single measure or a single kind, so a single dimensional output. Okay, and what are we referencing here? We're talking about a sphere on the outside, a hyperbolically bound on the inside structure, but the structure is, you can imagine a connection, and then a connection, and a connection, and then a little bit out this way. But that from here to here is made up of 1, 2, 3 things, right? But it represents a transform that goes from here to there. A single transform with a direction, even though it's made up of more than one thing doing it. Okay, what we want to know is, what are all of, that's a simplified thing, right? But if you had the whole system, what are all the pinpoints to pinpoints connections? Which way do they go? How many are there? And now I want to ask every constant of nature, do you have a relationship with the thing I just asked about? Okay, the partial partition structure of this hyperbolic system. Do you have a relationship with it? I'm just going to search on Wolfram Alpha to see. And we're going to ask every single constant. And we're going to eventually find, well, I'm about to show you now, the pattern that we found, the pattern that's revealed. But just to make it really clear, what this means is we need now to know the partial sets that give us single dimensional outputs. So I can, and they have to be plural. So I'll put them in parentheses. 1 plus 2, that's a one-dimensional real number. One-dimensional real number, so the output's a one-dimensional real number. So this one works. I want to look every constant in nature. Do you have a relationship with this partition piece of our whole partition structure or not? And I should note, I could have put a minus sign throughout all of these instead, and it's still true. So I also need, when I write that one down, I need to write down 1 minus 2. So these are both ones on our list. All right, that was just from this guy. What about 1 plus 3?
That'll give us a complex.
Yeah, the 3 and 4 are both complex numbers. If this is the first time you've seen this, you probably wouldn't know that, but we've been going through it for a while. So these two are one-dimensional numbers, and these two are two-dimensional complex numbers. So 1 plus 3 gives you complex output, so it doesn't work. We want a one-dimensional output because we're talking about what are the single transforms that this system makes. Just name them all. That one's not a single transform. 3 plus 4, complex plus complex, they happen to be in mere symmetry complex ones, so they cancel it out, the complex feature, and they come real. So yes, we also want 3 plus 4 and 3 minus 4. Cool. We can keep going through the list, and if you have no idea because you're not comfortable with them, you just plug them into the computer and ask, what's 1 times 2? What's 2 times 3? Is it one-dimensional or two-dimensional, and so on. You go through the list and get all the one-dimensional outputs, which now is a list of the partial partition structure of this hyperbolic space. Okay, all right. And that list, let me throw a couple more in. You can have the 3-part ones. You can have Je1 plus Je3 plus Je4. You can also have Je1 minus Je3 minus Je4. And so on. That list is important because you're going to see it now. It's mainstream to the structure we're revealing. All right, here we go. We're going to switch the screen. How about that? There we go. All right, we're starting on this column here in the middle. Starting with the speed of light. Okay, and as you can tell, this whole column is made up of the partition parameters of Je1 minus Je2. Still. Watch all the way down here. This is all Je1 minus Je2, and then a couple with the Je1 plus Je1 2. The whole column is just 1 and 2. Okay, let's look to see. We have left and right hand sides. You can usually tell there's a set of parentheses here on the right hand side, right? It starts here for this one. They always have the box ending on the right hand side. And then we have a left hand side. The left hand side we call the external construction. The right hand side we call the internal construction of our hyperbolic space. Now for the speed of light, the left-hand side is made just out of the intersection of the Planck length divided by the Planck time. right? The two different boundaries. The first one, the smallest, highest resolution, and the next define the fastest speed that you can move through the system. That kind of makes a lot of sense, right? On the right-hand side, reflecting the internal structure of the same boundaries, okay, the inside wall of the hurricane, of this specific part of the hurricane, is this side. And this is the partition part of the whole structure that it's referencing, this little small part right there, and it's shaped on the Giesecke manifold. That speed is literally taking the square root shape of the Giesecke manifold. Why is that? Why is there a connection there? This is the fastest possible speed in reality, and it's happening on the smallest possible manifold. That makes a lot of sense. Now, what if it were to go on something that wasn't the smallest manifold? Then it would have to blow up or implode. It couldn't be balanced. This smallest manifold is the smallest way to do something and stay balanced, to continue to persist, not to destroy yourself. So out of all the things that atoms make, because atoms are the things that are in self-balance, out of the things that atoms make, this is the fastest propagation speed, and it goes along the smallest geometric balance boundary that can be balanced. Great. There's another constant of nature, has different dimensions, where the meter is in this equation. The meter, the base, the second base in the construction is called the meter. And it's part of the constants of nature. Now, a lot of people have been told that the meter is a random unit, right? It's a man-made unit of length, like the foot, and it's just a base because we had to pick one, and more people settled on that than the other one, but it doesn't have any inherent meaning. Now, if you study the constants of nature, of course, you wouldn't believe that, but it might be an eye-opener to many people to realize that the meter, the kilogram, the Kelvin, the 5 bases are literally part of the constants of nature, the built fixed features of the world. They're not arbitrary parts. They're intrinsically important parts. They are the basis of logic in the system. They're not things we picked. They're things we were forced to by discovering the bits of logic, the constants of nature. The whole reason it's difficult to update the measurements by CODATA is that these 5 bases are in relationship to each other. So if you change one, you have to check all the relationships to the rest to see if it really screws things past measurements and find where the changes are best balanced. It's kind of complicated. All right, but the meter is part of that. Okay, part of the conversation. And here, the meter has a relationship to the Giesecke manifold. All right, if you plug in the number for the Planck length, divide it by the plugged in number for the Planck time, and then you times it by 1 plus the square root of the Giesecke constant, times by J1 minus J2, and then the box is the Planck length times by the Planck mass over the Planck charge squared. Okay, all numbers that we have out does any digit you want. If you plug that in, you get the number for the speed of light. Right? You get not just 299,792,458, but then you get the rest of the digits that you want. How many do you want to ask for? Because you have an exact closed form that predicts them. And it gets all of the ones we know exactly right. So that's the same story for every constant on the poster. That's the process we're going through. But what I want you to see is when we look for the pattern in the constants of nature via the partition structure of our fixed finite hyperbolic space with a Planck mass gap, we see some sort of pattern pop right up. I hope you're seeing some commonalities. Let's follow the right-hand side here. We get 2 over the delta phi Eigenbaum constant, again, 5 times. And then we get 2 alpha phi Eigenbaum constants, which are married to the delta phi Eigenbaum constants, if you know those two. They come together in any system. And then we get 1 over the Lemniscate constant, times by the same J parameters. Well, let's note, once positive, and 18 times negative. That's quite a pattern. Then we get 3 positive connections between 3, and this still involves lemniscates and pies. Let's go back to the left-hand side out here and look for a pattern here. Here it's simple between these two. We can see what's going on. These two are married together, of course, and then these 3 have a pattern, right? And both of them are giving us the structure of Ramanujan's first continued fraction constant, which at least we have some sort of notion of what's going on there. Divided by a circle every time. You wrap around a circle every time you divide and so on. All right, but then now we start our connection here. Our relationship now is between 2 pi and the meter, the joule and 2 pi. Let me pause for a second and try to explain the joule along with all the other composite dimensions. The base units are just these 5. But if you put more than one of these together, like you saw in the speed of light, we put that length and time together, right? So then we get a speed. It's a new notion. It's a composite notion of more than one kind. Here's the base composites that are referenced in here, so you wouldn't get lost by them. The joule is 2 meters, so meter squared, multiplied by 1 kilogram. And I'm talking about the meter twice. The kilogram divided by the seconds twice, okay? So that's what a joule is, and it's a unit of energy. As we go down this list, we're seeing relationships between circles and the meter, circles and the joule, circles and the electron volt and the joule and the meter. Here, a circle and the electron volt. Here, not a circle, but a relationship between these 4 things, joule, meter. We also have derived units. Derived units are like the inversions, because of the double cover, of the units. Okay? Derived units are these. Instead of seconds, we have megahertz. And a megahertz is 1 and 6 zeros inverse seconds. Okay? A femtometer is 0.15 and then 15 zeros and a 1. 10 to the negative 15 meters. Exactly, by the way, after that, it's all zeros. After this, it's all zeros. Or point and then all zeros. Okay, and there's another one called the electron volt instead of the coulomb. So instead of seconds, we get megahertz. Instead of meter, we get femtometer. Instead of coulomb, we get electron volt, megavolt, gigavolt. All right, so we got 5 derived units from 5 units. And we have composite units that are more complex interactions of these base units, okay? But all of them are really just coming from here. All right, oh, another thing to note here before we move on. Notice that the derived units are all exactly base 10 numbers. Important thing to notice.
And so far we have a Fibonacci sequence. 0, 1, 1, 2,
Yeah.
3, 5.
Keep going. What about it?
Next is 8.
Mm-hmm.
Is it important that it's...
Yes, absolutely. Absolutely. The Fibonacci sequence is absolutely central. In fact, it's the natural division sequence, right? A lot of these things are referencing the natural way to divide. First, you're one thing, and now divide. Now you're 2 things. Now divide. How many things? And keep going. Yeah. Okay, so back to this. We had our full structure. We're referencing partial structures. I want to make that more obvious to your eyes. Here's a set of partial structures. We went from here 2, 3, and 4, and we dropped the 1. So it's not the whole set here. And now we're looking at all these plus, plus, minuses, plus, 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 all in common. And this is the pattern that pops out. Well, maybe we should talk about that one. That's a good one to talk about. Let's talk about this pattern. Here, it's quite long. This is the molar mass of the electron. This is the molar mass of the proton, the molar mass of the neutron, the molar mass of the muon, the tau. This is of the atomic mass unit, so the molar mass of carbon-12, molar mass of the deuteron, the helion, the triton, an alpha particle, and then Na is Avogadro's number. Okay, all of those constants, those fixed features of the world, are using only what? We're using the Planck charge and the Planck mass in our divisors every single time. Every single time it's Planck charge, Planck mass, Planck charge, Planck mass, every single time, okay? And up top, what do we have? Well, in this case, where it's a molar mass of the electron, we have the mass of the electron. Here, we have the mass of the proton. So the top one changes in reference to the one name that it is, but the left-hand side is exactly the same every time. Exactly the same.
What's that left-hand side?
This might be familiar to recognize as a thing fixed into the primes. This is a feature, 6, very specifically, 6 over e to the Euler-Mascheroni is built in both the gamma function and the prime structure. Okay, so this is a prime division structure between these mass boundaries. And guess what? It's all of the mass boundaries. It's all of them. It's all of the, starting from electron all the way out. We don't have the quark ones, we have all the outside ones, the deuteron, the helion, the triton, outside ones. Connecting in one simple prime structure way. So yeah, the Fibonacci numbers are very related, because that's also in that conversation. What's on the right-hand side? Well, it looks like there's a pattern on the right-hand side too. We have the exact same J1 squared plus J3 squared plus J4 squared on all of these. And how many of those do we have, by the way? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Interesting, because one of them is molar mass of carbon 12, and it has a 12 in it. There's some sort of self-similarity system happening here. Another thing to notice is all of them on the right-hand side are multiplied by 18 times CQ. What's CQ? No, that's CU.
Okay. Yeah,
CQ is the QRS constant. I had never heard of it. This is how we would go about that. We put in QRS constant, and then it shows you what the number is. Cool. But first thing, root of zeta of 1/2 and x over 2. It's a little interesting to me. I mean, I don't know if you've studied the zeta function and the mystery there. They're central to this whole story. So that's interesting. But what we want to do is we want more information. So let's go to the page. It's all about this constant. Okay. So I'm trying to give you an overview of how I would figure this thing out, right? QRS constant seems to pop in the pattern for all of those. Now I'm really interested in it. What is it? Well, this guy, Quinn, investigated a class of N, stands for whole number, coupled oscillators, whose bifurcation phase offset had a conjectured asymptotic behavior of sine of phi, approximately 1 minus C1 over N. There's an experiment at N here, the number in your system. So with an experimental estimate for the constant as this number. Rather amazingly, Bailey later was able to find a closed form for C1, so give you the exact digits all the way out, right, as the unique root of the zeta function in a two-dimensional argument. The first dimensional is 1/2, where all the zeros lie, and the second one is 1/2 z. We can put in what do you want for z in the interval from 0 to 2, where zeta is the Hurwitz zeta function. So this is an asymptotic limit of the division structure built into the zeta function, interestingly. Interesting, right? And the zeta function is also central to the prime conversation, obviously, right? And you were bringing up the Fibonacci sequence, which is central to that conversation. It's all part of the story that's being revealed here. But these are the clues. This is the ways we're uncovering the clues. We're starting from physics, getting the list of our best measurements. We're looking for the pattern that those measurements match to what the hyperbolic structure of our finite hyperbolic space. Okay. Now, from that, we're not claiming that we're currently done and everything we have is currently right. What we're trying to do is now understand the pattern, go through it. If we find improvements and so on, fine, great. But the goal is to completely know what it means, to completely see something we couldn't see before that will empower us to now engage with the structure of reality in a way that we didn't know was there. Okay, the same way that all of science has transitioned so far. You can never see it ahead of time. But here we're going to use a new tool, and we're using the actual central structural heart of science. We're using measurements, right? We're using measurements and looking for the pattern in them. This is what we do in science. We're always looking for pattern. But here we're looking for the pattern in the fixed features of reality, the actual things that we know so well out to the measured measurement accuracy. Yeah. The facts that we have in physics need to be explained, not washed away. They have to be accounted for in the final story. So we're trying to get there by looking at the features that need to be accounted for, looking all the way out, every digit that they have, and the error bars, which is a really great thing. You get to play the game of science exactly. You have a confidence measure given to you. You don't have to play that part. You don't have to wishy-washy guess or try to figure it out. They have error bars for you, and you know that you can take only so far outside those error bars, and the further you go out, the less likely you think it matches, right? So you know how to narrow the search for the story. You know what you're trying to search for. But in order to do it, you have to take on the giant task of staring at every single constant of nature there is, the data point. Let's look at that. Let's go to CODATA. All right, here's a specific page on the CODATA website with the official listing measurement of the electron mass, 9.109383739 with an error of 28 on the 39. Okay, times 10 to the negative 31 kilograms. Now remember, the unit kilogram is a unit built into the features of reality, into the constants of nature. And this is in reference to that unit. So the electron is telling us something very specific about how the base of mass is naturally dividing. Because it's in reference to the kilogram, and the number is exact. The number that you're finding is going to be exact. And this one is sloppy with a 2/8 slop on the last two. right? And then that 2,8 defines plus 28 is plus 1 sigma. Minus 28 is minus 1 sigma. That's your error range. Now, 1 sigma isn't the limit of how far out you can look. In fact, the way we can tell that is, let me show you some of the changes in the last system. So here, the molar mass of the deuteron. Here's more information on it. So the same exact equation I was showing before, but before I was just showing you in the poster the equation. Okay. Here we're defining everything in the equation, where G1 is the first hyperbolic partition constant, E is Euler's number, this is Euler-Mascheroni constant, the gamma. This is the deuteron mass, the Planck charge, the Planck mass, and the QRS constant. So all these things now have names you can look up on Wolfram Alpha or online very easily. Okay, these are the official names.
This is Wolfram Alpha, or this is your?
This is my file so far of the data. Yeah, but if you look down at the bottom, so define all the constants in the paragraph here. But if you look at the bottom, we see at the bottom row the CODATA 2018 measure. This was the specific listed number and the size of the error bars to that number. And then you look to see, okay, now it's this, it's moved. And you can ask, how far did the move happen compared to what you said the one size error bars were? Okay, which were 61 in this case. And in this case, you can see the change by 4.28 sigma. Okay, so it gives us some sort of notion of what range is acceptable for our changes in this the game we're playing right now. They're playing it out 4.28 sigma here, so at least that's okay. I'm telling you that because at first I was playing very, very conservative. To me, I thought 2 sigma is starting to be very suspicious, so I wouldn't really look anymore, or I would just knock it off my list. And now that this thing's changed so much, I'm like, oh, okay, I'm looking out to 5. All right, so that's the kind of information we have listed on these things. When you look them up on, let's look at the deuteron molar mass. So new search here. Deuteron mass, deuteron molar mass. Okay, this is how it's listed. Okay, just this string of digits with an error bar on those last 2 digits and the dimensions. You can click in some cases here on the symbol and it gives you a relationship. Oh, it's equivalent to Avogadro's number multiplied by the deuteron mass. Huh. Let's go back and look and see if that makes sense over here. All right, back here on this, we're looking at the deuteron molar mass again. Okay, and we're comparing it to this one. All right, well, it says it's the same thing, except for this one times by the deuteron mass. Let's see, 6 over Euler-Mascheroni, 6 over Euler-Mascheroni. G1 squared, and, oh, yeah, QP on the bottom. Oh, yeah, oh, in this case, it's exactly in every digit, exactly the same, because the right-hand sides are the same too. Yeah, so that makes sense. The deuteron mass is Avogadro's number times by the mass of the deuteron. Yeah, that's exactly what we had. All right, in fact, it kind of makes sense now what all of them are. All of these molar masses are Avogadro's number times by the mass of the individual one. Interesting. Okay. All right.
And it also tells us the basis for Avogadro's number. That's quite interesting.
It really does. In fact, so this QPMP is a mole. When you put the charge boundary and the mass boundary together, you've made a mole. Or the thing we call in physics a mole. Okay, let's look at another list here. Let's go to the very first column. There, nice and big and gorgeous. And the first things I want you to notice, Planck's constant, reduced Planck's constant, and then Planck's constant. These two guys are just a relationship of the length boundary, the mass squared, the mass boundary divided by the time boundary. In our structure, there's just Planck boundaries, and on the right-hand side, the internal balance of that intersection is being made from the square root of the zeta function, the Riemann zeta function, zeta of 2. Okay, zeta of 2 is pi squared over 6. But square root of the zeta of 2, j theta squared. Now, j theta is the radial component of j3. If you look at j3, it's got x and y components because it's a two-dimensional number. Okay, but you can also change it into a radial description and have an r and a theta to describe it. If you do the r theta description of 3 and or 4, j3 and or j4, then you get this j theta number. So j theta squared in every case. Notice we didn't start with a j theta single at top. There's no 1 power theta. It's an interesting thing. They're always at least paired connections. There's always these two things together. All right. On the right-hand side, the pattern is pretty obvious because they're identities except for the plus and minuses. The only thing that changed until, oh, now we got zeta of 3. Now, isn't that a gorgeous set already? I got to say, I really got to say. There's a cool thing that happened recently. I didn't know about this one until a few days before the conference because I didn't know about E1. E1 is an energy associated with the hyperfine transition frequency of cesium-133. That's what this guy is. So there's a certain energy that's a constant energy that was an important thing, like the electron mass is a certain mass that's important. This is a certain energy that's important in the bifurcation structure of reality. Okay, he knew about it. I put it in there and bam, this one fits into this column. I had that whole column missing one. You could kind of tell it was missing one because when you counted, there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There was 11 of those and then 2 of these. Seemed kind of weird. Like 12 would be much better since we've got 12s and 14s everywhere and the bunchings of stuff. Like, man, and then finally, near the end, we finally found this energy I didn't know about. But here's what it did. There's, since we're composing all of this structure out of only 5 boundaries, the Planck constants, and each of those things are modular forms. They have a rotation and a scale involved, but a number of pieces that they're breaking into. So there's a modular whole number associated to each one. It turns out then that on this structure, on the outside and the inside, we're going to have 44 degrees of freedom on the inside because the Planck time has 44 as its power in its structure. It has 44 ways it shows up. So there's going to be 44 degrees of freedom that are all in the Planck time boundary, right? But there's going to be 44 numbers out on this side, on the right parentheses, that are different from each other. There's going to be 35 on the left-hand side because the Planck length boundary has 35 connections in it. So since this is a constant I didn't know about, it now bumped my list to 36 on the left. I'm like, that means one of them is definitely wrong. I got to go through them and which one's here, which one shows up the least? I'm going to be more suspicious about it and just go through them again, right? So it tightened up the system a lot. It really helped to know that there was one more there. So anyway, that was my point.
So Pat, maybe to clarify a little, it's basically there was kind of a gut hunch there that within the internal and external boundaries there should be a limited number of constants that we would use, typically mathematical constants within our construction.
Yes. And the thing I want to call attention to right now is, other than the Planck constants, what are the things that show up on the left? And what are the things that show up on the right? And which ones are in common? Turns out we get 35, 44, and 18 in common. How many division boundaries do you have for the charge boundary? 18. So that takes care of the first 3. Time, space, and charge structurally. Interesting. We were looking for that pattern because it was more than a hunch. It was necessary because our boundaries have to be modular. Why? Because they're persisting over and over and over. There's no other option. So if they're modular and they have that whole number structured to them, then that whole number must represent 44 ways it fits itself together and 35 ways it fits itself together in its modular action. So I knew that had to eventually be, but the delight was to see it happen. We could be at a stage in history where you needed 7 more significant digits before the pattern was revealed. We could have been there, but no, we're finding fantastic pattern already. We do have a lot of significant digits, and it looks like from the story we're revealing so far, it may be that 14 significant digits is the furthest it actually goes in the structure. It puts together 7, it puts together 7, but then the thing has now come back on itself. There's no more than that, which would explain, would make sense of a lot of it, like why are we only knowing the constants in nature out to at most 14 significant digits? Some of them are 9, right? But the best we got is 14. Why is that the cutoff? That could make sense of that. Anyway, we're at a stage where the pattern is here. We need to make sense of the pattern, but we need to vividly make sense of the pattern. We need to be familiar every time you see the TP, you're remembering, oh yeah, that's the boundary of the time base. That's the small little millions and lots of pieces that are all doing their thing, but trace out the boundary of all of them. That's that one. And it's fitting against the other ones, of course. And what we want to do is see how. But right now, we know what that piece is talking about. And individual pieces. If we get the individual pieces, we can start to understand how they're communicating and how they're relating, what they're doing to each other. But we also want to note how many times are they doing it. The things you want to first pay attention to are the things that happen the most often, right? The big swaths in the pattern, because that would be likely to be the easiest part of the story to tell. Let me swipe down real quick here on the rest of this column just because it's gorgeous. The constants you will notice are, we have the zeta function in the system, we have pi in the system, we have the base units on this side, the coulomb, the second, joule is a composite unit of the base units, the electron volt's a derived unit, we have the special energy as a constant that's important, a numeric constant that's important in this scaled hyperbolic division structure. Electron volt, another derived unit. But these are all just those simple fixed relationships. Note, if you make a list of how many things do we have so far in this whole 36 in the first column, Tesla's a new one, it's not a very big list, right? Here, PUP, the universal parabolic constant, that's the sibling to pi. Do you know what I'm saying when I say that? You believe so? Okay, so you do too? Okay, we've done that enough. Good. Yeah, defining a parabola. Yep. And then domino tiling constant on the right here. If you've never heard of it before, look it up. It's also connected to the Fibonacci stuff. This is the plastic constant. Okay, we'll get to that one, but it's got an interesting connection to the golden ratio. It's like another version of the golden ratio, except for with threes. And this is the fixed point of the hyperbolic cotangent, a fixed point like a Lagrange point in hyperbolic space. Unitary hyperbolic space. There's its fixed point. And we're now down, if you've noticed, at the bottom is 8. So we got all the way up to 8, and that's as far as we went. But we haven't collected, there's 36 equations here. We don't have 36 parameters on the left. You notice what I'm saying? There's a lot of connection going on, a lot of pattern grouping up here. All right, if we continue on the next one, we don't add a lot to each one. In fact, as I'd already told you, 35 total parameters on the left, 44 on the right. Okay, I actually have a suspicion that there's a couple changes still. There's 3 changes I want to do. Maybe we'll do them together. But what I want you to start seeing is these are incredibly short equations. Look at the gravitational constant equation. The gravitational constant, according to this pattern, first of all, notably has 2 siblings that are really, really related to it in the sense that on the inside, they are identical. Okay? There's 3 outside expressions of this same inside connection. And what is that inside connection? It's 3-dimensional in our radial hyperbolic sense. Okay? So 3 R's, filling out 3-dimensional space. Okay? But with what? The continued fraction constant. Not Ramanujan's first continued fraction, just the continued fraction constant. The simplest one. Okay? Really interesting. What does the continued fraction do?
It's a method for just continuing to iterate. If you had one whatever number, you would just continue on and on and on. You could just go on perpetually if that was a thing.
It could go on forever, but it's the method to look to see for the lowest common divisor. Okay? So you have a structure and you want to break it up and you want to find what's the smallest piece. What's the piece of the Planck time boundary in this structure, for example? It's the lowest, it's breaking up structure. If it's finite, it'll bottom out and have a bottom piece. And that bottom piece, the remainder at the end, will be your smallest piece that will be compatible with the whole structure. Okay, so here we got the continued fraction constant reaching out into the largest domain of things. Okay, but it's the constant that tells us just how we simply divide things up in the continued fraction way, all the way down to the smallest piece of the structure. But it also tells you that you're expecting now it's going to be finite, not infinite. L1, the first lemniscate constant, that's L divided by 2. There's a lemniscate constant. Actually, let's do a little bit on those because they're going to be quite important. Good to get more familiar with them. Let's do red.
You referred to the degrees of freedom as the power. Is that an accurate description?
As the power? Oh, the number?
Degrees, yeah.
Yeah.
The power, that would constitute a degree of freedom?
Yeah. Yep. Mm-hmm. Yeah, when you square something, then you have one expression and then you have a second expression. So there has to be another degree of freedom it's expressing in. So yeah, when you cube it, now there has to be a third and so on. So when we make the XY plane to characterize any 2-dimensional relationship, That's what XY plane's for, right? First we say the things we're putting in relation are X and Y. And now the graph shows us the relation maintained between them, right? The function. Let me go to -1 here and +1 there, and this of course is 0. There's a hyperbola. How do I want to draw the hyperbola? In fact, let's use the computer to first draw it. All right. So here's just the unit hyperbola, right? Crosses through 1. And we're connecting points. Well, here the focus is fixed there. What are we doing? We're taking a line, a straight line, and just connecting it somewhere to the hyperbola, and then wrapping the line. And it flips like this, right? Just watch the line. It's flipping, it's touching here, now it's touching there, right? And eventually it touches way on the opposite side now, and now wraps over there. But if you now track the central point, it carves out the graph of the hyperbola, or sorry, of the lemniscate, of the unit lemniscate. Okay, it goes all the way to 1, it goes to -1. But watch, it doesn't do it uniformly. Watch how the red line moves. Fast at the edge, slow at the middle. Real slow down here, right? And then real fast there, and slow down here. Okay, gives you some intuition about...
That's not a sine wave.
No, no, not a sine wave shape. It's a different one called lemniscate. Yeah, but it's an inversion curve of the hyperbola, right? That's what it is. It's just the inversion curve. Remember, we're talking about the inside wall and the outside wall. These two are bound by inversion.
Because technically that's going off to infinity, so that it reaches.
Yes. So we have a hyperbolic structure we care about, and the inside balance of that gap, at least part of it, is going to be one of these. It has to be because it is the inversion of it, right? We don't get to pick it, it's just there. All right, so that lemniscate, called the lemniscate of Bernoulli, it's a very specific one, we care a lot about. It's got an equation that's very interesting. First, we have equations for a sphere, x squared plus y squared plus z squared equals 1. That's the equation for the unit sphere, right? Should I plug that in, or is that very familiar for everybody? Here, you can graph that into Wolfram alpha, and boom, you just get a picture of a sphere. Or, let me write that here, sphere. Or we can change x squared plus y squared minus z squared, change the form like that, equals 0. And this gives us our traditional conic structure of the hyperbolic space. Okay, notice how it's algebraically in relation to the unit sphere. We can also change x squared plus y squared minus z squared. All the ones with the minus here will be the hyperbolic versions of the spherical one. Equals -1, and we can do x squared plus y squared minus z squared equals 1. So we have 3 options for the right-hand side here for that connection, and all 3 of them define the 3 surfaces of hyperbolic space. All right, let's see, which one's which? Sphere, cone, two-sheeted. Okay. All right, now let's look at the equation for this, for the lemniscate. It's x squared plus y squared equals x squared minus y squared square rooted. In here we got the exact same structure on the left-hand side for all of these, so it's in the same family, right? But there's no z in this one. So the first consequence is what? This structure lies in the xy plane. It's a 2-dimensional structure. It's a boundary, just literally just the 2-dimensional boundary that we drew here. It doesn't have surface like that. Okay. Another thing that's important is that in this specific lemniscate, the full distance all the way around is an arc length, and that arc length is s. That's the symbol we have for it. If you cut s in half and just talk about one petal, then it's L, the lemniscate constant. If you just take 1/4 to from here to here, or from here to here, or from here to here, they're all the same, right? All the quarters are the same, then it's L1. And if you take pi over s, that equals L2. Those are Those are the 4 lemniscate constants. And they're all just part of this picture. So pi is one to circles. Lemniscate has all 4 of these, but they're pretty easy to see. At least I think they're pretty easy to see. Another feature. Oh, now why is this thing so exciting? Well, when we broke up circles, everybody knows that circles are very important, right? Structurally, when we break up the unit circle, you could say the unit circle is x squared plus y squared equals 1. That's one way to do it. Or if you do it in terms of sines and cosines, sine squared of theta plus cosine squared of theta equals 1. Or could have put x in there. Okay, then we can do it that way too. This is the traditional ways, right? Now, when we break up the unit sphere or unit circle, in terms of sines and cosines, what are we doing? Yeah, we literally broke it into sine waves and cosine waves. It's now, if you put them both together, they draw the circle. But you've got 2 things that are component into the circle. All right, when we do that, we do it like this. We got and another one starts right here. Like that, right? Sine and cosine wave. Let me draw just one of them because they're exactly the same except for the off shift, right? Sine and cosine wave have the same features except for their offset. So let's just do one for now and say here's one sine wave. All right. What are the features of this wave? It's the unit wave, right? What are the features it carries? It has an amplitude of what? What's the height here? 1. Okay, that's an important number. That's why we call it the unit wave. All right. So also down here, -1. Okay, that makes a lot of sense, and this is 0. All right, so it's related to 1, -1, and 0. Huh, kind of like that. But we have more features. We have another distance here. Or you could even say this one there. Right, this is 0 there, and what's this here? This is pi, and this is pi, or 2 pi. So in the unit wave, we have all these features, the numbers 0, 1, -1, pi, and 2 pi. And one more incredibly important feature that was always missed when I was going through my education. So I don't know if you got it mentioned. There's another one here. It's the actual length of this path. There's an arc length. Like this one has an arc length called S. This sine wave has an arc length. The cosine wave has an arc length. They're identical, but they have an exact value. Shouldn't they be something important in our geometric story since they are literally the way we break up circles? Right? Okay, it's known. The arc length of this is 4 pi divided by S plus S. When we divide up the unit circle the classic traditional way into sines and cosines, into unit waves, we're already invoking the existence of this lemniscate. Right? If you ignore that feature, it's pretty easy to miss that, but that feature is not really ignorable to me. It's the one I see first. All right, that's what I wanted to say, that the unit circles, the unit lemniscate, the unit hyperbola, and in both forms, the unit cone, all of these are married in a very direct, beautiful way in geometry. Right? So the lemniscate constant, pi, S, L1, L2, Gauss's constant is 2 pi over S. The ubiquitous constant is, there's 2 more of them, we'll put it on a list. So GGA, Gauss's constant, equals 2 pi over S. And then we have CU, capital U, that's the square root of 2 times pi over S.
When you're talking about energy, wherever you are on that sine wave is your phase.
Mm-hmm.
Phase is a really important thing, particularly when you're talking about energy.
You're right. So great. So this thing has a cutoff of a phase too, right? The whole point of it is that it has a range from 0 to 2 pi, and then you're back at 0 in the phase. Yes, good point. Very important feature of the wave. In fact, that was the waveness of it. Yeah, good. Okay, the thing that's mostly missing in the story today in physics, I mean, we already characterize space-time hyperbolically. That's what we do. That's what Einstein did, right? That's Dirac equation characterizes things hyperbolically. But the thing that's missing in the story is an understanding of the actual scale parameter of the hyperbolic space and the partition structure of that hyperbolic space, the way it's breaking up. So the exact scale is important. In this structure right here, no matter what scale you have, notice, you would still get pi. No matter what angle you make the cone, you can still slice the cone and get the pi built in there, right? And no matter, since it's hyperbolic space, no matter what scale you make the cone, there's always a scale you can zoom into to get the 45 degrees. And that 45 degrees hyperbola that's built into there gives you the fixed universal parabolic constant. Right? All these constants are just constants of hyperbolic structure. Some of them don't depend on scale, like pi, so they're easier to find, and others do depend on scale. The part that's really missing in the story is all the scale parameter parts. No one's written the story of hyperbolic space in a way that picks the scale yet. So I think that's what we're doing by picking our mass gap scale, and then our partition structure with that mass gap reveals a pattern. And so now the idea in my head is to see the intersections of those boundaries, not to go from the algebra to the geometry. Right? I mean, algebra is algebraic geometry, but to have the picture, the geometric picture of what the algebra is saying. And that should help see if we have any contradictions or any flaws in the actual structure so far. Anyway, so that caught up to, I think, where we're at today. And the goal now is to look at the pattern we found, debate ones we might not like, look at the best patterns and see if we can make sense of them, but then move on to the discussion of how does this mean we get to then interact with the world in a new way? How does this new information facilitate us to do something new? That's the thing we need to step up into in our mind, right? Because it's going to be a new thing. It's something we've never done before, so maybe never even imagined before. So that's hopefully when we're staring at the language of reality, the language of physics. These are literally the structural components, the atoms of language in persistence. Right? All the things that persist must contain these connections. So these are the rules for persisting. And if we learn the language of persistence, we're actually learning nature's true language, right? There might be components of the language we speak now that really map well or maybe don't. But there might be ways of thinking in that language that are way beyond what we're thinking now. And that could reveal things that we have access to that we don't understand now. Anyway, that's my goal. And I think we're now, tomorrow we'll have the poster printed. So it'll be much easier to stand up and talk about it on the wall. Yeah, but meanwhile, what I want to do is try to get you at least familiar with the lexicon on the poster. I want you to know what all the things in the legend mean, or at least have been a little familiarized with them so they're not scary, right? You got to make them friends first, know what they are, and then you can talk about the relationships that these friends are in once you recognize them. But if you can't read them, they're just intimidating. So that's the goal at this point for me, or entertain questions that you already have so we can try to sharpen the productivity of how we do that together. Okay, so question time.
Well, starting at the very beginning, Dirac's equation, are you talking about a very long thing that goes on and on forever? Or can you tell me what the Dirac equation is?
The Dirac equation, just setting up the symmetric exchange in hyperbolic structures. So he just assumed projective structure is the way to go, because it's the only way to make a logical closure on your logic. And then assumed, well, if that's how it's closing, then there has to be a unitary scale to the closure. There must be. And so he's just wrote the equation down and then said, this must exist in nature using the constants of nature. And then people found the constants to attach as the scaling parameters that work. It literally works under the scaling of the constants of nature.
What did it look like? Was this very long thing that he wrote?
Oh, I can actually show you a whole video. And the video that'd be much more effective to answer the question. And the whole video had a lot of diagrams and graphs and animations. But in the thing, it basically shows you that the Dirac equation is characterizing the rules of hyperbolic space via this space. You're using the mass of the mass shape as your rules.
So what shape?
The mass boundary, the double sheeted hyperboloid is the base of mass, right, in the hyperbolic structure. And the Dirac equation is actually characterizing the square root of that mass boundary, which half, so just one. That's what it characterizes in the structure. And it says there has to be unitary scale. Everything has to invert and close on itself, so it has to have a unitary scale. And then we just search for the scale in which reality actually matches that. And we found that the actual constants of nature define that scale. So you keep the same equation, you just have to scale each term by a constant of nature, and it works with the speed of light and Planck's constant and so on, yeah.
So
and
Thad,
electron mass.
So Thad, how did you come about finding that gap? Were you looking specifically for it, or?
No, not at all. I was given the equation of the hyperbolic partition equation almost in the way it came, but without any gap. It was rewritten differently, and I rewrote it the way that made more sense to me, but then asked, the big thing about this equation is that it's a solution, or one of its 4 solutions, was real close to the square root of the fine structure constant, okay? Real close. In fact, it gave us several digits accurately. Not all of them, but several. And more than any other equation. And the equation was simple, so I was interested, right? At first, that's all I understood. We have a simpler equation than any other way that people can try to get there, and it gets more digits right. The next question was, well, if I put in the right answer in x instead, in the variable, then put an x on the other side, just plus x. How much does this whole thing have to change to get the right answer? And when I did that, put the x on the other side and solved, the number that popped out was the Planck mass, right? The value of the Planck mass, all the digits beginning in the right power. So, and that's a huge clue to me. So at that point I was, okay, we're onto something here. I'm starting to understand. We got a hyperbolic structure. We need to define a scale. And here it looks like the scale that works if I need to define the fine structure constant correctly is the Planck mass. I think we're on an approach that might work somewhere. Let's continue going, because it unveils more accurately as you stare closer at it. Anyway, yeah, so it was kind of by accident, but it was a huge surprise and very exciting. You can do that on your own, of course. You can just solve for it. So 1 over x plus x cubed over 2 pi. And then you set that equal to, minus some mass gap. All right, well, if you put in the square root of the fine structure constant for x here, here, and there, and solve for, make this the variable and solve for mass gap, then the value will spit out to the Planck mass. Okay, and remember, this structure itself was connected to what? To the hyperbolic figure 8 naught. It's the external expression that inverts finitely on itself of the internal gap, the smallest internal gap system you can create in hyperbolic space, held up by the smallest manifold. All right, next. Mike has a list of good questions.
Well, you've answered some of them. It's simple math. I don't know what I to the I power is. I mean, I can visualize I on a Descartes, graph.
Yeah.
But what is
Okay, I have cool things we can say about that. That's a really good question. So anything that's unfamiliar, I is familiar, but I to the I, what does that mean? I you can think of as a 90-degree rotation.
Yeah.
And I raised to the I is going to be 2 90-degree rotations that are in 90 degrees to each other. The rotation plane of one and the rotation plane to the second one are also in 90 degrees to each other.
So are we in 3-dimensional space then?
Yes, yes, yes. In fact, and the I to the I to the negative pi over 2 means we've also twisted it, so we're closed the 3-dimensional space.
One more time.
I to the I, that means 2 rotations that are 90 degrees, like the cone in the middle.
Yeah.
But raised to the negative power over 2 means we've twisted it. So the cone this way and this way are twisted opposite ways. All right, so he asked about what is I to the I. Let's get some more ways of writing that. Here's a bunch of them we should look at. Let's start here. I mentioned before Gauss's constant, s over 2 pi, and Cu is square root of 2, L2. These ones that you might have heard. Here we go. I to the negative pi over 2 is also equal to this entire thing. You might not know what that is, but you recognize s raised to the 2 pi. This other guy raised to the 2 pi.
S is
our full lemniscate.
Oh.
Yeah. Divided by 2 to the 3 pi here. Right? I like it this way. I like this way of writing it here. Okay, which makes you really interested in the Weierstrass constant. Notice the Weierstrass constant. Weierstrass? Weierstrass. I'm not sure exactly, but it's like that.
Name?
Yeah, the guy's name. Yeah. look, the lemniscate constant and the Weierstrass constant, both to the fourth power multiplied by 2, gives us I to the negative I.
And the Weierstrass constant is the simplest fractal, more or less?
Yeah, yes. Weierstrass constant is the constant for the simplest fractal. It's actually really gorgeous. But I want you to notice now, the simplest fractal has a direct connection, when you raise it to the 8th power, to e to the pi. Look what happened. I to the I is just the square root of e to the pi. Right? Square root of 4 is 2. Square root of L to the 8 is L to the 4. Square root of Weierstrass to the 8 is Weierstrass to the 4. The square root of e to the pi is I to the negative I.
That's interesting.
Very interesting.
And what is I to the negative I? Just the other direction?
Yeah, with the inversion. Okay, more ways to rewrite and try to get insight into what's going on here. Here's maybe a way. 4 pi equals 8 log of I to the I to the negative pi over 2. So same whole thing, take a log of it, square root, 8 times you get the 4 pi. So there's a lot of direct connections here between the most interesting parameters we care about in geometry. But also, look, gamma function relationships. That's what I wanted to say over here. There we go. I can talk about all of these other constants in terms of the gamma function also. Here's S. Gamma squared of 1/4 divided by the square root of 2 pi. L just goes down, right? So they're directly related to the gamma function. Right? Now that we know, we care about the unit circle, we care about the unit sphere, we care about the unit lemniscate, and we care about now all these lemniscate constants, which means we intrinsically have to care about the gamma function itself. The gamma function divides via these lemniscate constants. This way, it tells you the exact rule. Interesting. Okay. Anyway, there's a lot of stuff I put together here to try to make my brain absorb it. There's another way to talk about all these things in terms of a continued fraction. Right? Continued fraction is the way we divide things up. If we divide things up in the way the E is, or 1 over 1 minus E, they're very related. The most interesting ones, to me, are, I'd say, pi over 2 and L over 2. Look, it's all 1's down here, and it's 1 and then all 2's down here. 1, 1, 1, 2, 2, 3, 3, 4, 4, 5, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, see what's happening? We're just skipping here we're doubling. We're 1 twice and then, or other than the first one, we then do 1 twice and then 2 twice and then 3 twice and 4 twice and so on. But here, other than the first one, we just count up. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So here we got 1 extra. So the lemniscate and the pi over 2, lemniscate and pi are dividing the world up together at the same time, but in slightly different ways, but very related ways. Ramanujan's first continued fraction, it's 0, and then all 1's on bottom, and each time up here, it's just another multiple of 2 pi. Okay? We rotate by 1 more multiple of 2 pi every time we divide. So we're getting a continued fraction, a division structure, looking for our lowest common divisor. But as we're doing it in this way, we're also needing to get a whole circle every time. Really cool. And remember that the golden ratio is the same continued fraction structure if everything is just 1's. So it's the thing that references the balance of the continued fraction. And interestingly, that balance lives exactly in, where did I put it? The gamma function. Because gamma of that balance, the golden ratio, thank you, plus 1 as the argument is equal to gamma of golden ratio minus 1. On opposite sides of the 1, they cancel, they do the same thing, they balance completely out.
And the imaginary golden ratio does the same thing.
And the imaginary golden ratio does the same thing, except for that it does it oppositely. Very interesting. The gamma function is balanced both via the golden ratio and inversely balanced via the imaginary golden ratio.
But that's another question. I mean, I know that the golden ratio is a ratio between 2 geometric segments of the line, right? A number. What's the negative gamma? The imaginary gamma golden ratio. What is the imaginary golden ratio?
What is it? It's a -1 to the 1/3, which means we're on the unit circle, and it goes up to about here. So this point right there on this unit circle is the imaginary golden ratio.
So instead of like,
It's 1/6 away around the circle.
Instead of the square root of -1, it's the cube root.
Yeah, and that's equal to -1 to the 1/3.
I mean, the golden ratio we have it. Let's take a rectangle, of a certain kind, and we have the ratio of the long side to the short side, right?
Uh-huh.
So I'm not translating it here to the circle. Yeah.
Oh, I see what you mean. There's lots of geometric ways to describe the golden
That's
ratio.
another way to describe it.
Right here. The golden ratio is A over B,
Yes, that's what I was talking about.
also at the same time A plus B over A. So when that relationship holds, you must have the golden ratio, right? And in fact, both of these are equal to the golden ratio. In the imaginary golden ratio, it's, make it a little bigger. It's exactly the same structure except for that we put a minus sign there.
Okay.
Yeah.
Interesting.
Uh-huh. There's direct relationships between all those. Also, if you look at the continued fraction form of the golden ratio, it's all just ones all the way down. The imaginary golden ratio is just -1s all the way down. Yeah. Okay. Fibonacci-wise, you were asking about Fibonacci. The Fibonacci structure is based on the golden ratio. Power of the golden ratio. Golden ratio to the n equals the one before plus the one before that in powers added together. But the imaginary golden ratio has the same rule, except for we put a minus sign there, we subtract them. So there's a Fibonacci sequence that connects both of these guys. So now the questions we're really after, what does this actually look like, is what we're trying to do.
In just one, you have basically answered, I don't know how many questions I've always had about angles. And so clear.
Well, thank you. That's our goal. But I think we can get much more clear with the picture, right? And then a manipulatable picture. Then we'll start to figure out things we don't even know right now. So that's my bet.
I'm looking at the shape more or less as a conceptual shape, but I can see.
Yeah. We want to see it now. Oh, that's a great thing you just said that. We want to see it now. I'm not recording, so we can switch. Oops. Oh, my pages are gone. Okay, there. I had a page up on algebraic geometry and manifolds and stuff. And it was talking about manifolds are really important in physics, right? But what we're really going to describe now and try to get imported in our head is what this thing is we're calling a differentiable manifold.
Right.
Okay, at first the scary words, sure. But once we have a differential manifold in our head, what that can mean, then we're going to fit this to this differentiable manifold. Differentiable means it breaks into pieces, and all the pieces, the way it breaks up, determines all the consequent actions, right? Everything's derivative from the breakup structure. There's no leftover gaps or anything. Anyway.
Is the lemniscape, is that basically the spin of the atom?
It's definitely part of the spin.
Okay.
Absolutely, yes.
Yeah. Okay.
It's also kind of fun that it also happens to be a figure eight.
Yeah, it's pretty. All right, so I think it's break time because I need a talking break, but that's the goal.